In this video, we're going to continue in chemical bonding, chapter 12, by looking at how you can use something called VSEPR, and I'll explain what that stands for, to determine the shapes of molecules. Now, before you watch this video, you will need to watch the video on how to draw Lewis structures, because the shapes we determine are going to be based on the Lewis structures. So, molecular shape is just the idea of having a three-dimensional shape around a molecule, because we draw our Lewis structures, and Lewis structures are two-dimensional. They don't have any angles necessarily. Well, they don't have any, like the way I draw it, it's all 180 degrees, 90 degrees, so we don't have any other angles than that. There's nothing coming out of the page. It's just lying there on the page. So Lewis structures just by themselves don't have to tell us about the geometry or what we would also call the shape. So we're going to use a model called the VSEPR model or VSEPR theory. And VSEPR theory, you can see right here, stands for valence shell electron pair repulsion. Valence shell electron pair repulsion. And you don't have to memorize what VSEPR stands for, but you do have to know how to use it to determine the shape. So the whole idea around the VSEPR theory is that the valence electrons involved in the bonding are all negative charge, and so they would repel each other. So the shape predicted would have those electron regions, either bonds or non-bonding, around the central atom to get as far away as possible. Now, one con about the VSEPR theory is it really can only be applied to one central atom at a time. So if you have multiple atoms that are in a chain or a line in an atom, in a molecule, you actually have to apply the VSEPR theory to each one, like they're each a central atom, and put it together like a puzzle. Now, for us, we won't have to be doing that because we're going to be looking at one central atom. But I just want you to know up front, for larger molecules, you don't really have an overall shape that's determined by a single thing. It's more like putting pieces of the molecule together. So the things that we're going to have to pay attention to, they're called, we call them groups. They're electron groups, and they will either be an atom, which is represented, is bonded, to a central atom, or lone pairs. So you're going to see once we get going, I'm going to be counting up how many atoms are bonded to the central atom and how many lone pairs. So let me just have you read this. So determine that, I'll unhighlight it again so it doesn't look too, maybe if I just circle it for you, read this. To determine the shape around an atom, and so we're talking about the central atom in our case, determine how many groups are around it. And so we're going to count how many atoms are bonded to the center and how many lone pairs. And then we're going to apply, I have a table for you to use. So on the right of this slide is the VSEPR handout that we have. And since we're only doing central atoms that have an octet and they're not exceeding the octet, we only will have these shapes. The table gets longer because it can accommodate for when you have more than 8 around the central atom. And so if you're going to go to the next level chemistry, you'll see that they add on more possible shapes. It all follows the same line of reasoning. So it's important in introductory chemistry to get this line of reasoning or how you're thinking about it down. So then when you have new things presented to you, you can apply what you've already learned. So let's go over this VSEPR handout just quickly, what each column means. In the lab, you'll also be doing it. So we have titles up here. We have what's called the electronic geometry. Let me change my highlighter to something even lighter, if it will let me. going to make it even lighter if I can. There we go. I just changed it. So hold on. I changed it. Okay. Excuse me. The electronic geometry, well, that makes it almost worse. It almost looks like it's whiting it out. Okay, I'm going to use my pen. Sorry. No, I will use a marker and circle it. So the electronic geometry is here. So the electronic geometry is the overall geometry, and it treats any of the groups the same. It treats lone pairs around the central atom the same as atoms. And so then you'll see there's two columns in the middle, and this is what we're going to be counting, the number of lone pairs and the number of atoms. And these are specific. It's not total, where these are what is around the central atom. This handout is available to you in Canvas, as well as you could have received a copy in class. Then over here, we have if we keep going, we have the molecular geometry. That is what we consider to be the shape. So when it asks about the shape, it's actually asking about the molecular geometry. Now this column here, I'm just going to draw a line through it right now. These are just examples, and these pictures right here, the sketches of the shape, are for that specific example. So the overall shape is generic, but they have put the specific example in to that particular shape. But if you had that shape and it wasn't the same elements, you could replace your elements into that shape. All right, so let's see how we're going to approach this. So the first thing you need to do is identify the central atom, which we know that's the one in the middle. So I'm just going to point to the central atom in this example as carbon. And then you need to evaluate what is attached to the carbon. So you need to count the atoms and the lone pairs so that are bonded to the central atom. So let's look at it here. I would count, well, let me get a different color. Okay, so I have it's moving. 1, 2, 3, 4 atoms that are bonded to the central atom. And listen, you do not care if it's a single bond, double bond, or a triple bond. They tell you to count the atoms, not total, the atoms bonded to the central atom. So this particular example has 4 atoms, and I'm just going to write this for our reference. And then the second thing you want to do is you want to look at the central atom. There's carbon. And you want to count any lone pairs that are on the central atom, not on a periphery atom, only on the center. And in this case, carbon has 0. 0 non-bonding or lone pairs. So this is a 4-0. So then now you go to the chart and you find there's 4 atoms. See, it says atoms up at the top, and that has 0 lone pairs. So the electronic geometry is tetrahedral. I'm just going to write EG. And then the shape or the molecular geometry is in this column, and it's called, oops, I was wrong. Oh, darn it. I hit the wrong button. You follow it all across. My eyes just got distracted. It's also tetrahedral. Now, if your homework just asks for the shape, that's going to be the molecular geometry. So how I have it drawn here, it actually, and in this illustration over here, the dashed line is supposed to be going behind the board, the solid line is supposed to be coming out at your face, and the 2 other lines are within the plane of the piece of paper. So it's trying to show you, I imagine it kind of looking like a tripod kind of thing that wouldn't have the exact right angles, but the correct angles, but it would give you a visual. Now in lab, you'll be building models, so you can kind of see how in 3 dimensions this would look. It's a little harder to see on a piece of paper. Now, you will notice that anytime the number of lone pairs is 0, the electronic geometry, which is on the far left of the table, is the same as the molecular geometry, which is the shape. So now let's look at the next one down. This is water. And so again, how you evaluate for the shape using the chart is you go to the central atom and you count how many atoms are bonded to it. And in this case, there's 2 atoms bonded to it. So I think 2 atoms. And I'm just writing it here for our purpose of instruction. And then you go to the central atom. Now this oxygen does have lone pairs, and I count 1, 2. So it has 2 lone pairs. Okay, so this is 2 and 2. So then I go to I'm going to erase this so I don't have too much writing as I keep going. Let me make my eraser bigger so it doesn't leave such a mess. So now you're going to look and you want to find things that have 2 atoms. Okay, I see this one, I see this one, I see this one. So there's lots of things with 2 atoms, but not all of them are the answer because it also has to have 2 lone pairs. So this one can't be it. This one can't be it. So it is down here. So this has an electric geometry that's tetrahedral. So anytime the electric geometry is tetrahedral, it means that the total things around it, atoms and lone pairs added together, are 4. So both the first 2 are tetrahedral electronically. The first one has 4 because it has 4 atoms and 0 lone pairs. The second one has 4 because it has 2 atoms and 2 lone pairs. But notice the lone pairs change the shape. So the molecular geometry here is called bent, or in the handout is called tetrahedral bent. So the student tutor that many years ago made this handout for us, she designated that one as tetrahedral bent because there's also another bent in a different place. So she was trying to distinguish the 2, and that's fine, but you may see in your homework that it would only say bent, and that's okay as well. So that water molecule is a nice bent water molecule. My Lewis structure looks linear, like it looks like it's a line, but those lone pairs take up space and push the hydrogens into an angle. In fact, lone pairs take up more space than the bonded pairs. And again, in lab, you will be making models of these, as well as there's a digital simulation where you can kind of see a digital 3-dimension. Again, I feel like the models are the best because they're in your hand, but there's different ways for us to try to see it. Now let me erase all my scribbles and then let's do the next one. You can always pause the video now that you have an idea and see if you can do the next one, and then turn it back on and you can see what I do. So I would look at the center. There we go. And so then I first see how many atoms it's bonded to. So that's 1, 2. Again, it doesn't matter that it has a double bond. That's not what we're counting. We want to count how many atoms are bonded to the central atom. So this one has 2. And then I look at the central atom and I want to look at how many lone pairs. Now notice I'm not counting all the lone pairs on the structure, only the ones that are in the middle, and that has 1 pair. Okay, so again, we go and we're looking for 2s, and you don't always have to circle all. I'm just trying to show you this would not be it because it has no lone pairs. Here it is, 2, 1. It couldn't be this one. This is 2, 2. So here we are. That now is an electronic geometry that's trigonal planar. A trigonal planar electronic only has 3 total things around it. You can also say trigonal planar. It's 2 different ways to say that. And then we come over here. This is also bent, but they might say just bent or trigonal planar bent. Okay, so that's how we apply this Lewis structure, this Lewis VSEPR work handout I call it the shape sheet, how we apply the shape sheet to our Lewis structures. So you have to have a Lewis structure first. So that would be the first thing that you would need to review if you have forgotten or did not originally watch the Lewis structure one. So I have a few more examples. And so I encourage you to pause the video, try to apply what we just learned, and then turn it back on, and I'm going to go through all three. I will go a little quicker than I did on the first page, simply because we've had an opportunity now to think about it. So, okay, pause if you want to. I'm going to start going. All right, so I would look at the center, and nitrogen has 3 atoms around it, because it has 3 hydrogens, and nitrogen has 1 lone pair on it. So I need a 3 and a 1. So here's my 3 and my 1. So the electronic geometry is tetrahedral. Remember, tetrahedral is anytime there's 4 things around it, whether it's atoms or lone pairs. Tetrahedral is for 4. And then it's trigonal pyramidal. So this kind of looks like a pyramid, and on top is the lone pair. So the lone pair, like when they name them, it's almost like the lone pair is invisible, but the lone pair takes up space. So it pushes those, in this case, the hydrogens down. So the molecular geometry is trigonal or trigonal pyramidal, like a pyramid. Whoops, but if I could spell peer, but I forgot my A, pyramidal. And these all have different bond angles. As a part of your lab handout, that you will use the simulator to see the variation in the bond angles in the different shapes. All right, so let's do HCN. We did this as a Lewis structure when we were learning Lewis structures. So again, you apply the VSEPR handout to the central atom. So I look at my central atom where I have my arrow, and I count how many atoms are bonded to it. This has 2 atoms. It has a hydrogen and a nitrogen bonded to the central atom. It doesn't matter if it's a single, double, or triple bond. We're counting the number of atoms that are bonded to the central atom, not the total atoms, the atoms that are bonded to the center. Then looking at carbon, I would be looking for any lone pairs on the central atom, because the whole VSEPR model is based on the central atom, and carbon has 0 lone pairs. So I needed 2, 0. So I see right here, there's 2, 0, and in both situations, it is linear. So it has an electric geometry that is linear and a molecular geometry or shape that is linear. If there's lone pairs on the central atom, it's not going to be linear. Like linear, it has no lone pairs on the central atom. Okay. Now let's look at this last one, which is one of our charged particles called a polyatomic ion, but polyatomic ions are ions that have many atoms, and those atoms are covalently bonded together. That's how we get a Lewis structure. They can form ionic bonds with other charged particles. So in this case, if there was a cation, it could form an ionic bond with it because it has charge. So it has both types of bonding going on, because it has a covalent bond bonding the nonmetals together, and then it has a charge, so it will have an ionic bond with the charged particles. But to do the shape of it, to treat the same way, so I look at the carbon, I see that there's 3 atoms bonded to the carbon, 3 different oxygens, and then I look at the carbon and it has no lone pairs. It's not a coincidence that carbon has 0 lone pairs in all of our examples. Carbon likes to form 4 bonds to complete its octet. It has 4 valence electrons, so it likes to share 4. So carbon likes to form 4 bonds, and really, I couldn't say always, but rarely has a lone pair on it. I'm thinking like carbon monoxide, it has a lone pair, but most of these types of molecules we come into contact, carbon will not have lone pairs. It likes its 4 bonds. So carbon, let's see, 3 atoms. So here's 3 atoms and 0 lone pairs. 0 lone pairs. And so the electronic geometry is trigonal planar or trigonal. I say trigonal, but some people say trigonal. That has 3 things around it. And then the molecular geometry is also trigonal planar. Remember, anytime there's no lone pairs on the central atom, the electronic geometry and the molecular geometry are the same. Okay, so here's one thing we can do with Lewis structures, and that is to use VSEPR theory to determine the actual 3-dimensional shape around a central atom.